Alright guys, so we've already checked the plates and tension. We've also checked our pulse and shear. So now as we don't have our pulse and tension, so we just have our pulse and shear, and we want to check the tearing and bearing. So according to the code, so to apply or to check for bearing and tearing, you have to apply this law 0.9 VB. And VB is actually the lesser of these two equations. One of them is 0.9, the edge distance multiplied by the thickness of the blade multiplied by FUV. And FUV is actually the tensile strength of the blade material. And this is, you can actually get it like, for example, we have 300 megapascal for our grade section. So it's going to be according to the table 440. So, and then you have also to apply another formula to get which one is actually the lesser, which is 0.9 multiplied by 3.2 dftb thickness of the blade multiplied by the FUB. So what is df? Df is actually the diameter of the bolt. Diameter of the bolt. So we have M20, which means df we having is 20 millimeters. So let's go to our question to see which one of this actually we're having. So first of all, we're gonna say the edge distance. We want to know the thickness of the blade. So we have two plates, and we have FUB. We're going to get it from the table. So this is the question. All right. Okay, according to the question now, we want to check, we want first the edge distance. So the edge distance, as you can see, is 35 millimeters. It's this one or that one, it's the same thing. So instead of we have 55 millimeters, we have as an edge distance. All right. So the other one, we have two thickness. We have the thickness of the top plate is actually 12 millimeters, and the thickness of the bottom plate is 10 millimeters. So logically, we're gonna take make analysis for the bottom plate because it's 10 millimeters. So we take the less because if the failure happens for the less one, so that's for sure is going to happen for the top one. That's for sure. So we're gonna take TB, make analysis for the bottom one, which is 10 millimeters. All right. So let's go to our Excel sheet and see how it's going to be. So this is, as I said, this is the formula. VB star is equal, must be less than 0.9 VB. And the edge distance we're having is 35 millimeters. The TB, now we have two of them. One of them is 10 and one of them is 12 millimeters. So we can actually make for both. So this is actually because of an Excel sheet. But logically, we're gonna go to the bottom one, as I said, because the formula is the same. The only difference is the thickness. So the lesser thickness is gonna be the more critical. As you can see here, when I did for the two of them, just you can see that the one for the having a less thickness is going to have a less force. And this is something logical because we have the equation is linear. We don't have anything. So we have 35 millimeters edge distance and 10 millimeters for thickness of the plate. FUB is equal to F ultimate. So it's according to how much the grade. And the question, we already say that our grade is 300 millimeters. So you can go here, we have a table and see, okay, so this is for the plate, 300 millimeters, it means F ultimate is equal to 440. Alright, so FUB is going to be 440 megapascal. And now we're going to apply for the first formula, 0.9 multiplied by the H distance multiplied by the thickness of the blade multiplied by F ultimate. And this is what we got for our tearing. So the first formula is actually for the tearing and the second formula for the bearing. And we already show you a picture about this difference between the tearing and bearing. If you want, you can see it again. Okay, this is what we mean by tearing, and this is what we mean by bearing. All right, so now it's almost the same. Everything is the same. That DF, as I said, we have M20 in the question, and for the balls, and M20 means 20 millimeters. So we're going to apply here the 20 millimeters. All right, so to make sure, you can go up and see. Yeah, M20 means 20 millimeters, which the one we're using now. All right, 20 millimeters. Now M20, DF is equal to 20. So and this is we have we can get our result. So now we have two results. One of them is 138, which is for the tearing, and the another one for the bearing is 253. So obviously that our plate is going to fail for the tearing first. So we're going to take the lesser, which is 138, multiplied by the number of force to see how much force can be carried in our plates. So we have 4 balls, so you just take the lesser, which is 138, multiplied by 4, and you get how much our maximum force can be applied. This is the maximum, and that's it. Now, for this one, we know that our bearing capacity or bearing and tearing capacity must be less than 554 to be able to be in a safe design. So let's now check all of them. Now we already make, as I said, aerial. We already make the blade tension. We check for the two of them. We have the upper blades and the bottom blades, and we find that the upper blades is going to fail on 428, and for the bottom blades is actually going to fail in 457. Means, and the tension to be felt is going to reach the maximum force we're going to have is 428 for the tension. However, when we go to the shear in the bolts, we find like the maximum force going to apply is 370. So that means the shear, the ball is going to fail and shear earlier than the blade is going to fail and the tension. And we move forward. We don't have a tension in our balls, as I said. We don't have a moment here. So we're going to go to the bearing and tearing. So in the bearing and tearing, we found that it's 554, which is the lesser of the two blades. Obviously, you can just make the thickness, take the lesser thickness, and that's it. But as we have an axle seat here, I've already designed it, so calculate for both them. So now you can see that the maximum force in that that we want to calculate in our question here, determine the maximum design end force is going to be in the tearing, which is 300 something, 370. So I can now write here that the maximum design force is 370 kN.